We're going to take a look at this function j of x equals the square root of x minus 2. Notice all of this is contained under the square root. And we're going to first start with the assumption that we are looking for real numbers. So our domain is going to be real numbers, our range is going to be real numbers, and kind of take a look at what happens with that. So typically I like on a function to start with -1, 0, and 1 to find points to graph. So I'm going to make an xy table for this and kind of look at points. Alright, if I take a -1 and I plug it into here, I have -1 minus 2 is -3. If I try to take the square root of -3, if I'm using a typical scientific calculator, it's going to give me something like a domain error or something like that, because you can't get a real number back when you take the square root of -3. So for the purposes of our xy table, we need to put in something like d and e here, meaning does not exist. So no real number is going to work here for a y value. So let's plug in 0 here. 0 minus 2 is -2. Again, we're trying to take the square root of a negative number, so that's not going to give us a usable y value. If I put in 1 here, I have 1 minus 2 is going to give me -1, and again, I'm not going to get a real number as an answer. The next thing that I try is 2. 2 minus 2 is 0. Square root of 0 is 0, so I actually get a real number for that one. If I put in 3 here, 3 minus 2 is 1. The square root of 1 is 1. And then putting 4 in here, 4 minus 2 is 2. Square root of 2 is approximately 1.414. If you want to be exact, you're going to put square root of 2 in here, which is approximately 1.4. And so we do have 3 points now that we could plot over here. So at 2, I'm at 0. At 3, I'm at 1. And at 4, I'm at 1.4. So I have this kind of a graph. The assumption was that we were looking for real numbers, which is what you typically see in a lot of classes, especially lower level classes. But what would happen if we said that complex numbers was allowed? I've made some extra notations here. We're defining the first one. The function f is defined from the real numbers to the real numbers. So we plug in a real number and we expect to have a real number out here for our domain. This next one, I'm going to define the same function j from the real numbers to the complex numbers. So I'm going to start in my x column with real numbers, and in my y columns, this time I'm going to allow complex numbers. And we're going to take a look at how this xy table compares to this xy table. If I plug -1 into here, I get the square root of -3. So this is going to give me I times the square root of 3. So this is a complex number. If I plug in 0 here, I'm going to get square root of -2, which is I times the square root of 2. Again, a complex number. If I plug 1 into here, I have 1 minus 2 is -1. Square root of -1 is I. And then nothing changes as I start plugging in 2, 3, and 4 here. So I'm going to get the same values here. So what are the changes? When we allow for complex numbers to be in our range, we get actual values in this y column. There's no y value that does not exist. Where over here, when we're only looking at real numbers going in, real numbers coming out, we had values that we couldn't get a real number for, so these did not exist. So this is the difference when you define functions on the expectations on domain and range. The domain, where you were expecting real numbers to go in, real numbers to come out for the range. So looking at a problem like this, if you're told to find the domain and the range, In this graph, these are all real numbers in this graph. This is an x and a y axis. So within this picture, this is only real numbers. This is what we did in the first XY table. So the domain can be defined as all the x values we can put into here to get a y out. So our domain, what x's are we allowed to put in here? Well, if you look over here, a critical point was right here, where the square root was forced to go to 0 when we plugged in an x, and so we took the square root of 0. That started when we plugged in 2. So x has to be greater than or equal to 2 in our domain to have something that we can graph on our Cartesian coordinate plane. So for our range, what y values were going to exist? Well, y values started existing at 0 and counting up. So y was going to be greater than or equal to 0. So the domain and range for this function in something that's graphable on the Cartesian coordinate system is going to have a domain of x greater than 2, a range of y greater than or equal to 0. So we include 2 here, we include 0 here, and that was found at this critical point here. If we allow complex numbers, these y values are not going to graph here in the Cartesian coordinate system. You can start graphing part of this in, well, you can graph this entire xy table on the Argand plane where you have a real and an imaginary axis, and so you can graph these points there. So this is a different geometry, essentially, a different way of looking at graphing points than what we have going on over here. So typically, in high school exercises, you're looking at the Cartesian coordinate system and defining the domain and range based on what you can graph. So let's make one final note about this critical point. How would you find this critical point if you're looking for graphing in the Cartesian coordinate system and finding the domain and range? Well, what you want to do is you want to take the expression that's under the square root and pull it off to the side. So we have x minus 2, and then set that equal to 0. And then solve this for x. So we're going to add 2 to both sides. This is our critical x value. If I plug this x value into here, it sends this to 0, and so I'm taking the square root of 0 and getting 0. So this is how we find this critical x value. We'll plug that in, we get 0 back, and so every number equal to this and greater, in this case, for this function, is going to give us something we graph, and these are all real results. Domain can be real, range can be real. Critical point here is 2, and then the output from that was the 0, so that defines your range. So this is a key calculation here in finding this critical point. Let's take a look at one more function. I want to look at the cube root function. So I have the cube root of x minus 5, and I want to take a look at what happens there. And we're going to look at the real numbers and expecting to get real numbers out. So we're going to define this function h from the real numbers to the real numbers. And we'll set up another xy table here. And again, I'm going to start with -1, 0, 1, and see what happens. If I plug in -1 to here, I'll have -1 minus 5 is -6. So I take the cube root of -6. If you type that into your calculator, it's going to give you a result. The cube root of a negative number is a real number. In a very precise way, we can just write the cube root of -6, or you can plug this into your calculator to get some decimal equivalent. So this is approximately -1.817, a real number. If I plug in 0 here, I'll take the cube root of -5, and I'll get a real number. If I put 1 in here, I'll have 1 minus 5 is -4, so I'll have the cube root of -4. So we continue to get real numbers. So that's a nice thing about the cube root function that doesn't happen with the square root function. One other thing we might discuss is there anything special that happens when I cause this cube root to go to 0? So we can pull this off to the side and set it equal to 0 and solve for x and see what happens. So I'm going to add 5 to both sides, so I'm going to have x equals 5. If I plug 5 into here, I have 5 minus 5 is 0. Take the cube root of 0 and I'm going to get 0, because 0 times 0 is 0, 0 times 0 is 0, so that works. I have what was my critical point in my square root. I still get a real number, it still works the same way, so let's try one number bigger. What happens if I put in 6? 6 minus 5 is 1, cube root of 1 is 1, so again, real number, it works fairly nicely. If I put in 7 here, plug in 7, 7 minus 5 is 2, so I take the cube root of 2. That's going to be a real number also. So this cube root function works really nicely. It doesn't generate these complex numbers that we had in the other problem, and so we don't really run into issues in this function that we had in the last one. Of course, all of these can be graphed, and so you can get a nice graph in the Cartesian coordinate system. So just a quick sketch, maybe not believe my diagram, but I have a x-intercept here at 5, 0, and I have a y-intercept here at 0, and this is approximately negative 1.7. So y-intercept here, x-intercept here, we have this kind of elongated S looking curve, and so that's what this gives me. So, domain and range. What x values can I put into this? Well, since this spans the entire x-axis, any of the x values is going to work. So x is going to be all real numbers. What's the range? It may not look like it, but this eventually goes out here, positive infinity. This is going to go out here, negative infinity. It's going to encompass all the y-axis. Eventually, it's going to be a slow grow, but it's going to work. So y is also going to be all real numbers. And so that's our domain and range for this function. Cheerful calculations.